Chapter 5, Factoring. Factoring is multiplying reversed is one way to explain it. Thus, when we have polynomials, factoring polynomials, first we have to really understand how we multiply polynomials. So, when we talked about in Chapter 4, I brought up several times that, there are some other ways you could probably multiply using like FOIL and miss some of the shortcuts that are going to become real important to recognize factoring opportunities or strategies. So we'll go through those again as we go through this, but like a lot of things in algebra, either you're going to learn it while you're working on the material, and you'll test well and you'll get good grades. A lot of times I see students who are like about a section or two behind, and I know you're going to have to learn this material to succeed in the next sections, and that's definitely what this chapter is about. A real solid understanding of Chapter 4 is going to be real critical before you get very successful in factoring. So let's look at this. And the first factoring is, there covers a lot of things that have to do with having a monomial or a single factor come out, and that's what mono means, one. So to factor a monomial, we find monomials whose product are equivalent to the original monomial. And like when we talk about division, usually when we're talking about math, we say division is the opposite of multiplying. Well, this is kind of similar to that. I don't think they use division words in this part because of usually all the negative thoughts that come up with division, especially long division. But we're actually going to do long division too in this chapter. So example 1 here, and they jump right into this. It says factoring. To factor a polynomial is to find an equivalent expression that is a product. Product means answer to a multiplication. An equivalent expression is this type is called a factorization of the polynomial. In other words, we're going to take a polynomial and we're going to take it and break it into factors, or factors mean parts of a multiplication. So we're breaking it into a multiplication of different expressions. So they go through and you can explain a lot with examples, just like a picture is worth 1,000 words. Examples usually are worth 1,000 pictures. So we look at this first one, like 15x cubed is, we could show this a lot of different ways of being factored, and that's what they're illustrating here. Is I could say, I could write this, because really this means 15 times x times x times x, or 15 times x cubed. You could write it a lot of different ways. Well, they say 15 I could write as 3 times 5. That would be the prime factorization of that. Prime means that the only factors of like 3 are 1 and 3, and 5 is 1 and 5. Definition of prime again is it has exactly 2 factors, or numbers that I can multiply together to get that same number. So thinking how 15 and x cubed can be factored, we can write this a lot of ways. In fact, I could write more than this. I could break this up. I could change order with the commutative property and associative properties, and I could write out that x squared as x times x, and so on. So that's what they're showing us here. But the other thing that too is very easy to forget is that I can take a negative times a negative and get a positive. So there's some negative factors that are available to us. And when we get into opposites and stuff like that, there's going to be some advantages to remembering how to deal if I could take out a negative 1 out of something to factor that. But that's what they're showing us right here basically is, yeah, I can write this same expression a lot of different ways in types of multiplications of these expressions. Every one of these, if you multiply them out, you'd get 15x cubed. Now when we have multiple terms in a polynomial, means many, or poly means more than one in this case. It has two or more terms, parts of the addition, which brings up, when we're talking about addition and multiplication, we're talking about this distributive law. So when I multiply, like we did in chapter 4, if I had 3 times this polynomial here with the grouping symbols, we would distribute that multiplication over all parts or all terms of that polynomial, parts of the addition. And I would say it's a pretty good idea to think of this as a negative z, right? Because that's what terms are, parts of an addition. The term here is not z, it's negative z, okay? So when we multiply, we end up with this expression here. They show it all broken out, and then we get 3x plus 6y plus a negative 3z, or minus 3z. Well, if we factor this thing, it would be take this resultant polynomial that we got from the multiplication. I would look at for common factors in each term, in each part of the addition. In this case, it's 3. And then I can factor out the 3. In other words, I can write this as 3 times x, 3 times 2y, plus a negative 3 times z. Okay? And then I factor out the 3. And so I could write that basically the reverse of that multiplication. So they're really kind of going through how do we multiply with the distributive property, and then how do we factor. Basically we're using the distributive property again, or law. Example 2, it says factor to the form of an equivalent expression for 8a minus 12. Now this, I think, is the best way to approach these kind of problems on a continued basis, is that if you prime factor every term, you're not going to miss any common factors. There's one unique prime factorization that will multiply to a given term. So in this case, 8a is really 2 times 2 times 2 times a. Now is a prime? How many factors of a are there? There's actually just 2 factors of a, 1 times a. Now it gets kind of weird because you're thinking, well, there could be numbers in there, but we're dealing with the variable just as it is. So this is the prime factorization of 8a. So 2 times 2 times 2 times a. That's the only way you can multiply prime numbers. These are the only prime numbers in this combination of multiplication that will give you 8a. That's what I mean by being unique. This covers all the prime factors, right? Well, if I do the same thing with 12, 12 is 2 times 2 times 3. 2, 2, and 3 are prime. So I have an illustration of basically all the factors, of prime factors, and then I can match up common prime factors. In other words, there's a common 2 and a common 2, or 2 times 2, which is 4. And if you do it this way, you will not miss any common factors because they just match up. It'd be very easy to look at this and say, hey, 2 goes into both of these, and just factor out 2, and then you get 6a plus, or excuse me, 4a plus 6 as in inside here, and it wouldn't be totally factored. You want to get all the common factor out you can, okay? So they see that, hey, this is 4 times 2a is another way to write 8a, and 4 times 3 is another way to write 12. So we can factor out this 4 because it's common for both terms, and we end up with 4 times the quantity 2a minus 3. Now most of the time you're not going to write this all out. You're probably going to do prime factorization. I'm going to see I have a 4 common, then you put the 4 out in front of the parentheses and write out your the rest of your polynomial inside. Now I check. It's definitely easier to multiply than it is to do this factoring in a sense. So I check what I ended up with, and multiply it back out and see if you get the original. Okay. And these cautions are always good to look at. These are common errors that happen. It's kind of like I wish it would work this way sometimes because it would make the problem easier. But we got to follow the rules, not find some easier specific way to deal with one kind of problem that usually is going to cause some errors. So in this case, you say if you have 2 times 2 times 2 times a minus 2 times 2 times 3 is a factorization of the terms 8a minus 12 is not a polynomial itself. Okay? We tend to think, hey, I just factored each part of this. I need to make it a multiplication of both of these, right? So basically the caution is understand what we're trying to do with factorization. And actually when we get more into solving equations, writing it out this way does very little to help me solve an equation that has this expression or work with this in applications. This does. I have some things I can do now to simplify and solve that weren't available to me before. So here's another example using prime factorization. And again, I like that they write this out. You're probably not going to write out your variable if you understand what x to the fifth means. But x, remember, x is your prime. So you match up the commons. In this case, we have a 2 that's common, a 3 that's common, x and x. So 2 times 3 times x is 6x squared. That is my common factor between these two. So I can write this as 6x squared. I just put this, and then what do I need? What's that leave here basically to multiply by? Well, I look back at my prime factorization. I got rid of these, right? So now I just have 2 times 2 times x multiplied, right? Or x to the third power. So I end up, that's 4x cubed. Same thing with this 30x squared. What did I use already in my, what did I pull out of my multiplications here? Well, 2 times 3, x times x. All that's left is 5. So I have a term of 5 here. Okay, so then I have this factorization of 6x squared times the quantity 4x cubed plus 5 quantity, right? Well, check that. Multiply or distribute that back out. Make sure you get the original expression that we dealt with. If you don't, then there's some kind of math error or factoring error, probably prime factoring error, okay, if you use this. Now, the largest common factor of the polynomial is the largest common factor of coefficients times the largest common factor of variables in all its terms. I like to read these every once in a while because, boy, they can spit out a lot of words at you there. But one of my goals, hopefully, in this course, and your goal too, is that you learn how to pick out or understand math languages. Translation from English to algebra, boy, there's a lot of it here. Factor, common, what does that mean? Largest. You know, you break these words out and go like, hey, these aren't complicated. It gets to be a mouthful when they put it all together. Coefficients, what are those? That's actually the number times the variable portion of the term, and so on in the variables. Basically, they explain that this largest common factor, how we get that in words. Like I said, the examples really tell you a lot, but you got to make sure you understand the whole process here and why we can do this with the distributive property and so on. So they go through these kinds of things, and they're also showing you this is something that can happen. You might do a lot of work and you don't prime factor and you say, hey, it looks like 2x squared is the common factor, and that's true, it is common, but it's not the largest. So I go here and I go, well, it would be 2x squared times 12x cubed plus 15. And then I go, oh, that's right. There's a 3 that's also a common factor between these terms. I don't have to start all over. I can just factor out the common and basically factor this one now and say that that is really 3 times 4x cubed plus 5. Now remember our laws about multiplication. We can break the parentheses between multiplications or change the order if we need to. Those are the commutative and associative laws. So I can change this basically and say I can take this multiplication of 2x squared times 3 and I get 6x squared. And then I multiply times this last factor, which is actually this addition here, this binomial, in a sense, two-term. Actually, I don't know if it's the proper term for that, but this is a polynomial. When you think about degrees, there's a couple ways of looking at that. Okay. Well, I still get to the same place that I wanted to, even if I just break it down into multiple steps. If you use prime factorization, this should not be happening to you. And that's why I like prime factorization methods, is you're probably going to save steps, which is also going to save you chances for error in math. So it's a good way to go, is to start with prime factorization. And again, they show us another example with more than two terms in the expression. And then they talk about this not being factored any further. I remember when you're talking about simplifying fractions, they say reduce it. And then when you can't reduce it anymore, it's in simplest form. I understand what that means. I've heard that language, and I've actually taught with that language. But the reality is there are no more common factors other than 1. That's when I know I am done factoring a multiple term expression. Okay. Well, let's look at example 4. Now I have 3 terms here, and they use prime factorization. Now remember that when we have 3 terms, all 3 of these terms have to have common prime factors to be able to use as a common. So they list out the prime factorization. A good way to get to these sometimes is to use trees. If you got any questions about that, it'd be a great question on email, or send that to me and I'll send you a picture of how to do tree prime factorization again. If you look up at Google, say prime factorization, I'm sure you're going to see some pictures of that tree model of prime factoring. So on. They just don't show it here in the book. But anyhow, here's a listing of all the prime factors of all 3 terms. We match up the common ones, okay? Which happens to be 3 times x times x times x, or 3x cubed, is common for all 3 of these. So I know I'm going to have this 3x cubed in front of the parentheses of my new multiple term expression in here. And then what do I have left? Now I wouldn't go back to say, well, 3x cubed times what gives me 12? Well, I can look at this prime factorization. These red ones I've used, what's it leave? 2 times 2 times x, or 4x squared. Same with this next term. I got 5 times x left, which is 5x. Now, I would prefer, again, I see a lot of errors around these negatives. You forget that it's a subtraction. I think you're going to have a lot more success if you change that to an addition, and then I would list a negative 1 times 3 times 5 times x times x times x. And the only reason they're not showing that right now is they're going to go through a special little section in this, or little part in this section about negative 1s and what do we do with that. But be careful if you do it this way. Again, I'll come back to that probably several times. I say I would rewrite this expression as 12x to the 5th plus negative 15x to the 4th plus 27x squared. And then I would list prime factorization, because negative 1 is a prime number. It has 2 factors. That's the definition of prime. It's negative 1 and 1. And, the definition of prime based on that 1 is not a prime number. That's why they never list that in here, okay? Because it only has 1 factor. So, anyhow, they list the primes. Careful about those negatives. Multiply back to make sure you didn't make a mistake. Okay, now they're going to go through quite a few different examples trying to deal, like these ones. We have multiple variables. We have an r and an s and an r and an s, and that so on. If you use prime factorization, It really literally is exactly the same process. I prime factor 8r fifth s to the second. I got 2 times 2 times 2, r times r times r times r times r. They should list them out. They only list it once because they know it's only going to match one. And then the s squared matches, so they already kind of know what's going to match up when they list this out. But if you prime factor this whole thing out, and I think when we get to you practice this variable matching, you're going to be able to do this in your head too. But if I use prime factorization, really no process is different other than I just have more variables, right? So we get 8rs squared is my common factor. So I'm going to have 8rs squared times something. Well, if I take this out, right, the common parts here, and which are here, and I prime factor that. See, I would leave the whole prime factorization of this 8r to the fifth s squared. They're just trying to show you maybe a different way of doing this. Well, that would leave r to the fourth left here, and then 2 times s times s times s, or 2 times s cubed. Okay, so that's the same thing here. They kind of write it all in red. I guess we could change it and match up the commons here. What's left, multiply it out. What's not used in those factors, that's going to give you what these terms are, and so on. Same thing, they go through this. I would check these examples out for sure. Now these tips are very good things. Just factor out the largest common factor if one exists. You should always look for that, because when we're going to get into more complex types of factoring, this is the simplest type of factoring, is look for this common factor first. And the common factor multiplies a polynomial with the same number of terms as the original polynomial. And 3, the factoring can always be checked by multiplying. Very good tip. We usually do better and are more familiar with the distributive law by actually doing the multiplications. Okay. Now, grouping is a little more, it's a degree of complexity that goes on top of the same idea. If I have this example 6 where I have x squared times the quantity x plus 1 plus 2 times the quantity x plus 1. Hey, the common factor here is this thing that's in the parentheses here. That's the same factor, right? So that's a common factor. And I can use the distributive property to say that's the same as this times that. They reverse the order just trying to make it more visible. But really, I can say that this plus this times these two common things is my factorization. Very powerful thing for more complex polynomials. Let's look at this next one where it isn't so obvious right away. Notice that you can kind of pick out this common factor. Let's look at this one. If I ever have 4 terms in a polynomial, and they're talking about just finding common factors, I probably have a grouping issue. Maybe if I group these things together using the associative property, because this is all addition, right? It's supposed to be all addition with us remembering what's going on with subtraction. Well, they group this first 2 terms and the second 2 terms together, because when I find the common factors here, which is x squared, I end up with x squared times 5x minus 1. And right here, if I find a common factor of 3, I get 3 times fx, well, 5x, minus 1. Hey, here, inside these grouping symbols are common now, or the same, and I can factor out to here. This factor by grouping is a tougher part of this. But boy, if you see this and get good at this, it can save you a huge amount of time, because like I said, we're going through probably the fastest and easiest types of factoring. As we get into further sections it's going to get more complicated, more steps. So if I can avoid those by using these tools, basically these strategies, I'm going to save a lot of time and you're going to save a lot of headaches. Now, we can still check this, right? Well, let's use FOIL. They say first in, first times first, outer times outer, inner times inner, last time last. And we end up with this new polynomial, which, hey, good, it matches the original. I was successful in that factoring. Okay? This method is known factoring by grouping. So they're going to go through a few examples like here. And each example they do usually has some kind of issue that a lot of times it's easy to forget. And that is the identity of multiplication. Right here is this first one. It says, what happens when I group these and I go, hey, I factor this and I get this x plus 4, and this is just x plus 4. What is multiplied by that so I can do the factoring, right? Well, remember, you can multiply 1 by anything. So what you do is you put in a multiplication of 1. And when we get to negatives again, this is going to be an important concept to think about. Because I need a number here to be able to pull into this new part of this multiplication. This 2x squared plus 1 I get here. Before I get 2x squared, if I don't put that 1 in front, I'm going like, what is the number? Well, it's 1. That's the identity of multiplication. I can always multiply by 1 and not change any parts of this expression. So, caution, be sure to include the term 1. That is why they did that example. This example here has some other things that can come up with negatives. And let's look at this this part here. You might group this, and I go in here and I got this 4t cubed minus 15. And they factor this and they say, hey, looks like we can group this like this, and notice that they decided to change the order of the addition with a strategy. And this, it looks easy when they, hey, why, you might say, hey, that's cool that they saw that and they did that. Well, this is the strategy stuff. Look for these things to do this, because when I find common factors in these groups or in this associative property portion, I'm looking for the grouping symbol to be common. Okay? So they change the order using the commutative law to rearrange the terms, and we end up with 4t cubed plus 20t squared minus 3t minus 15. And they go, well, 4t squared is a common factor between here, and I get t plus 5. You'd look at this and you might say, well, 3 is a common factor, and I get plus 3 times negative t plus negative 5. They don't match. This is the part about negatives. Remember that if I took out a negative 3, is what they did here, is they took the minus 3 out, or the plus a negative 3, and then I get positive t plus 5 again. The goal here is to find the strategy to match up these things so I can continue to use the distributive law and factor this thing. Okay? And then that's what they're saying here. Factoring out a negative 1 to reverse subtraction. So if I have a subtraction issue, let's look at this. I'm going to jump down and we'll come back to what this is saying again. Look at this example. I got t squared, t to the 5th minus 5t to the 4th plus 10 minus 2t. Well, they group them in the same order there. And they get this t to the 4th times the quantity t minus 5 plus 2 times the quantity 5 minus t. Well, what they want you to see is this and this are the opposites of each other. In other words, if I take a negative 1 times this subtraction, I get the opposite order, don't I? This ends up to be negative a times a is a negative a. And then a negative 1 times a negative b is a positive b. So I got negative a plus negative b. That's one of the reasons I don't like subtraction, is too is you got that order dependence, right? Well, what they're trying to show you, if you want to change order, I can do that with factoring out negative ones if I need to change this order. So that's what they do. They say, well, hey, if this was in a different order, these two things would match. So let's factor out a negative 1, and you get negative 1 times t minus 5. If you actually multiply that again, think about that. Don't go by this too quickly. Look at this and I say, well, negative 1 times t minus 5, if I multiply that, I'd end up with this right here. So this replaces that. And why do I do that? Because now these match up. And then I have, make sure that I treat this as a negative 2, not a positive 2. Okay? And then I can do this next part of my factoring to do that. This working with negatives, I hear it a lot. Well, my sign was just wrong. No, that's a big deal. Negatives, especially when we're working in this world here, is be very solid on how your negatives work, negative ones, and checking that. And then they check this problem that we thought we got the answer to, and they multiply back and make sure. And in this expression, right? But the other thing we can do is check by evaluating too, which is this is a good strategy. I like to think about this as doing a simpler problem. If I end up with these two expressions, right, and I want to find out if they're the same, if I put the same value in for the variable, I should get the same number come out of both of these. If there really are truly equivalent equations, or expressions, excuse me, is they should have the same result if I put the same variable in. Now, I would be strategic about what I'm not going to put in here like 22/7 or something like that in for x and deal with a whole bunch of multiplication by fractions and all that kind of stuff. I'm try to take a number that's going to make this easier to work out. So they put in 1. You probably should avoid zeros, which would be okay in this case, but sometimes bringing in a 0 value can have some issues, especially if we have a division in there by that variable. As soon as you divide by 0, everything goes undefined, so you don't have a good check on this thing. So in this case, 1 looks like an easy one to work with. And you know, I might even take negative 4, but that would be a problem there too, because what does that do? Negative 4 would give this be 0, and when I multiply these two out, I'm going to get 0. I worry about zeros coming in here because just a caution to do that. They might give you a false evaluation of these things. So they put 1 in, they do the calculations, you know, the first expression is 2x cubed plus 8x squared plus x plus 4. Well, they put 1 in for x, they get 2 times 1 cubed plus 8 times 1 squared plus 1 plus 4, I end up with 15. If I go to my factored one, put 1 in here, I get 15. That's a pretty good indication that we did this okay. You know, I could multiply this back and do that. But this does bring up some good points. It's very easy when you're factoring to check it, because the reasons you factor it the way and check it wrong, if you made a mistake factoring, it's very possible you're going to say, when I check this, the reason that I factored wrong is I got some wrong thing that I'm doing with the commutative law. Replicate that wrong idea backwards, basically to check, and you end up thinking you got the correct answer. Well, this will probably take care of this, because once I have numbers in there, all I have to do is worry about order of operations, which hopefully is not going to be an issue. And they go into graphing calculators, which we're not covering in this course and stuff. Here's the exercises.